Post on the classroom parking lot in the back of the room. So if ever you have any questions on homework problems, feel free to put them down there and a video like this will get made. So we got page 253, classroom exercises number 19, and then page 254, written exercises number 26 and number 28. Okay, let's get started with the classroom exercises, number 19. So this one here was kind of a proof of a theorem that they're kind of getting us to think about here. It actually doesn't really come into play really until question number 20, which was also on your homework. So we proved something up here and had you think about what you got proved down here. So I'm actually going to fill in what gets proved in this down here first, and then we can think about it and think about all the steps that would justify it. So here it says exercise 19 outlines a proof. Okay, complete the statement of what is proved. In an obtuse triangle, the square of the side opposite the obtuse angle. Okay, so angle 1 is an obtuse angle, so the square, right, k squared, the square of the side opposite the obtuse angle is, and it looks like in number 19 we're looking to prove that the square of the side opposite the obtuse angle is greater than the sum of the squares of the other two lengths. Okay, so this is very similar to one of the Pythagorean Theorem plus theorems that came up in the section immediately following this one, where it was proven that if we had a triangle, then the square of the largest side was larger than the square of the sum of the squares of the other two sides, and then the triangle needs to be obtuse. So I kind of wanted us to get thinking about that one a little bit before we ended up proving it next section. Okay, so anyways, let's look at this specifically, because this is where the question was, question number 19. Okay, so in this figure we have measure of angle 1 is greater than 90 degrees, measure of angle 2 equals 90 degrees. Okay, so I want to mark up that 90 degree angle. That is a 90 degree angle, so we'll make it a right angle. So here we see two sides of the obtuse triangle congruent to two sides of the right triangle as shown. Okay, perfect. So that means that side A is congruent to side A here, length A. And we have length B, and that's repeated here, length B right here. Okay, so what we should immediately see is that we have two congruent sides, and those are, right, they're congruent, so they're the same lengths as each other here, and the same lengths here. But then we have an angle, right? And this angle here, angle 1, is larger than angle 2 right here. Okay, so this should get us to remember something right away. And that is going to connect to over here, step 1. This is making the statement that K must be larger than C. This distance K here larger than C, okay? And what we should remember from chapter 4 is that we had an SAS inequality theorem. Okay? What we proved then, right, was that if we had two sets of congruent sides, or two corresponding sides, corresponding sides are congruent here, or corresponding sides are congruent here in two different triangles, and the included angle, right, the included angles were different than the side opposite the larger of the two included angles is going to have to be larger than the side opposite the smaller of the two included angles. Okay, so we know that K has got to be larger than C. This guy here, the hypotenuse of the right triangle, is smaller than the side opposite the obtuse angle in the obtuse triangle that has, right, this same side lengths here. Okay, so that one is SAS inequality theorem. Okay, so to get from step A to step B, these connect immediately together, right? We don't use a diagram for this at all. We can just justify this algebraically. You might have been a little bit stuck on this one because this looks kind of like a property of proportions, but if you review our property of proportions from our textbook, you don't see anything about squaring, right? You don't see anything about that. So what they're looking to kind of get you to think about here is actually maybe some other properties, you know, or just reason through it at all. And I'm going to actually go beyond the textbook here to this reason, okay? This is just something that I looked up online, you know, they assume you've seen something like this in textbooks before, but, you know, textbooks aren't a big thing nowadays. But this is a property of exponents applied to inequalities, okay? So here, let's think about it. We know that we have K, we know that we have C. K is greater than C, okay? So if K is greater than C, then we'd actually know the square of K would have to be greater than the square of C, okay? And there are a few reasons for that. One, kind of the biggest thing, is that we would know that k would have to be a positive number, right? In geometry, the nice thing about all the distances we have and angle measurements as of now that we have is that they're always positive numbers, okay? So if k is a positive number, let's say it's 5, just for the sake of demonstration, okay? If this is 5 and that's 3, right? K is greater than c. If we had 5 greater than 3, right? If we square both sides, the larger positive number, right? If it got squared, right, is still going to be larger than the square of the smaller positive number, okay? That is a law, right, of algebra, okay? So here, this is a property of exponents applied to inequalities. If we have any positive numbers, so as long as we're dealing with only positive numbers here, okay, let me cross this all out because it's kind of confusing. If we have two positive numbers and one of those numbers is larger than another number, then the square, or anything taken to a power, right, a power, here C, that's positive. If we take the positive number to a positive power, it's going to be greater than the smaller number taken to the same positive power, okay? Repeated multiplication with larger positive numbers is going to be bigger than repeated multiplication of smaller numbers, okay? So this here, kind of cheating because it's not really in your book. You would just say property of exponents. Exponents and inequalities. Okay, this one here, this one's pretty obvious. This one is just over here, that's c squared have to equal a squared plus b squared, and that is the Pythagorean theorem. Okay, so we have a, we have b, we have c. Finally d, okay, so we have d here. Well, we've already said that k squared is greater than c squared, and c squared just happens to equal a squared plus b squared. Okay, so through a property of proportions, or actually, this would be substitution, come to think of it. Okay, I'm crossing this out. And if we read substitution, right, what we're really just doing right here is that we've already had this statement here, k squared is greater than c squared, and we know that c squared represents this. So what we're doing is we're taking this expression here, which equals c squared, and replacing it into that inequality. And that's just substitution. Okay, we don't really need to worry about this too much. All right, hopefully that helped. Right, might have been a little bit confusing to write down, but really not the biggest of kind of justifications here or proofs that need to be written. But they just really wanted to get us to think about this before doing the Pythagorean Theorem plus, where we prove that if the squares, square of the largest side of a triangle is larger than the squares of the two other sides, then the sum of the two other sides, then we know it's a triangle. Okay, so let's look at the other problems.